بسم الله الرحمن الرحيم. بنرحب فيكم في المحاضرة رقم 10 في الديجيتال سيجنال بروسيسنج أو في الإجراءات الإشارية الرقمية. اليوم رح نتكلم في موضوع جديد اللي هو يعني بدنا نبحث السيجنالز من from the frequency point of view، من ناحية الفريكوانسي مش من ناحية التايم دومين، من ناحية الفريكوانسي دومين. الموضوع يعني بجوز بعضكم يعني اللي اخذ سيجنالز اند سيستمز دائما بيعرف انه في مقابل الفورير ترانسفورم في الكونتينوس دومين في شيء اسمه فورير ترانسفورم في الديسكريت تايم دومين، فاحنا رح ندرس discrete time Fourier transform اليوم. So our topic today is the discrete time Fourier transform. The discrete time Fourier transform. اختصارا احنا بنسميه DTFT. Okay. As a definition, the discrete time Fourier transform وراح نعطيه الرمز x of e j omega of a sequence x of n is defined by x of e j omega. So we didn't put it x of omega. In some books you will find it x of omega, but it's more representative to put it in as a function of e to the j omega, as you will notice in a while that all the results are function of e to the j omega or multiples of this value. So x of e j omega as a definition is equal to the summation from n equals minus infinity to infinity, the discrete sequence x of n multiplied by e to the minus j omega n. So this is simply the definition of the discrete time Fourier transform. So transformation in frequency, omega is the discrete time frequency, x of e j omega is the resultant, this is x of n is our discrete time sequence, and this is the definition of the Fourier transform. Let's take a very simple example, example 1, and find the DTFT, discrete time Fourier transform of x of n, where x of n is equal to delta of n. So we take the very simple sequence, which is one single sample function. So my delta is n equals 0, you have an amplitude of 1, this is your delta of n, and all the values are 0 up to from minus infinity to infinity except for n equals 0. So this is my delta, it's an impulse. So our delta of e j omega, so we take uppercase delta, Latin delta, delta small, delta uppercase is equal to the summation from n equals minus infinity to infinity, delta of n e to the minus j omega n. And this is by the shifting property, this is equals e to the minus j omega times 0, and this is equals to 1. So delta of e j omega, actually, if this is omega, it's a constant amplitude of 1, and this is delta e j omega. And you can see that, you know this from signals and systems, that all the functions, if you have an impulse, you have a DC for the frequency, and the opposite is true. If you have impulse in frequency, you have a constant value in the time domain. by duality. Okay, let's take another example. Example 2, find the dTft of x of n equals to 1, 2, 3, and we'll take 0 here at the moment. So x of ej omega for this sequence is equal to the summation of x of n e to the minus j omega n from n equals minus infinity to infinity. At the time being, you have only the non-zero ends are 0, 1, and 2. So you will plug here x of 0, e to the 0, x of 1, e to the minus j omega, x of 2, e to the minus j 2 omega. So this one will be 1 plus 2 e to the minus j omega plus 3 e to the minus j 2 omega. So this is our function. Just to take this one, example 3, if my x of n equals the same, 1, 2, and 3, and you have here the 0, then your x of e j omega equals to 1 times e to the j omega plus 2 plus e to the minus j omega. So this is your x of e j omega for this x. For this x, when the 0 is shifted. So this is negative index. You put here minus 1 multiplied by minus, so e to the j omega, positive. This is the index n equals 0, so e to the j0 is 1. And this index is positive, so n equals 1. So it is e to the minus j omega times 1, which is equal to e to the minus j omega. Okay. I'm going to take a different example here, example 4, and we consider x of n equals to alpha to the n mu of n, where magnitude of alpha is less than 1. So we need to find x of e j omega. So x of e j omega equals to summation alpha to the n mu of n e to the minus j omega n from n equals minus infinity to infinity. Now if we apply the mu, which is 1 from n equals 0 to infinity, so we can take it out and put it in this form, alpha to the n e to the minus j omega n. But now this is n, this n goes from 0 to infinity. So we replaced mu of n by its values. Negative values equal 0, positive values equals 1. So you end up with this from 0 to infinity. Now I'm gonna combine alpha with the exponential n, put it this way, alpha e to the minus j omega, the whole thing to the power n, from n equals 0 to infinity. Now this is definitely equals to 1 over 1 minus alpha e to the minus j omega. Okay, why? Because the magnitude of alpha e to the minus j omega is equal to the magnitude of alpha, which is less than 1. E to the minus j omega, it has a magnitude of 1 and an angle of minus omega. So it's cosine plus j sine, and the magnitude is cosine squared plus sine squared of omega, which is equal to 1. So this one, e to the minus j omega magnitude is equal 1. Okay? So this is the answer. And you can figure out that, okay, in most cases, or in the usual cases, why we call x of e j omega not x of omega, because notice here, this is e to the j omega, e to the minus j omega, e to the j 2 omega, 1 over e to the minus j omega. So it's actually a function of j omega. And this is why we put it in this form. Okay. What we need to notice here is that, generally speaking, x of ej omega is a complex quantity. So a complex quantity is usually represented by its real value and imaginary value. Okay, so x of ej omega is a complex quantity. So we say that x of ej omega is equal to x real of ej omega plus j x imaginary of ej omega, or x of ej omega equals the magnitude with an angle theta, where theta of ej omega is equal to the argument of x of e, the argument which is the phase angle. Okay? Okay. Before we go to the inverse of the DTFT, usually DTFT is a unique transformation, which means that x of n is totally has unique transformation, and if you know the transformation, you can go backward and find the time domain discrete time signal. But before we go to the inverse of this transformation, I will discuss with you two important properties of x of ej omega. Two important properties of x of ej omega. The first property, and you can see it from all the functions and the examples that we have here, is that although x of n is discrete, x of ej omega is a continuous function continuous function of omega. So the first property is that x of ej omega is a continuous function of omega. Although x of n is a discrete, but the function that we will get, x of ej omega, has a real part, imaginary part, it's a continuous function. The second property is that x of ej omega is periodic with a period of 2 pi. The period here is equal to 2 pi. Okay, for the continuous, it's already obvious. But for the periodicity, let's check out the periodicity of the DTFT. To check the periodicity, I'm gonna take, so to verify the periodicity, we will take x of ej omega plus 2 pi k. So we'll take multiples of the period. So we said that it's periodic with a period of 2 pi. So I'm going to take x of ej omega with omega plus 2 pi k and do the definition. So this is x of n e to the minus j omega plus 2 pi k times n, from n equals minus infinity to infinity. Distribute the parentheses here. So I'm gonna put it in this way: x of n e to the minus j omega n times e to the minus j 2 pi k n. This one here is always equals to 1. It's multiples of 2 pi, whether it's positive or negative. E to the j 2 pi is always equals 1. Its cosine multiples of 2 pi, which is 1, plus j sine multiples of 2 pi, which is 0. So the answer is always real, and it is equals to 1. So this is equals to x of e j omega. So if the function with multiples of its period equal to the original function, so the function will be periodic. So the periodic with a period of 2 pi. Yeah, okay. Okay, let's take a look now. I'm going to make use of the periodicity and the shape of the transformation itself to make a conclusion and get the inverse of the function, the inverse of the dtft. So the definition of x of ej omega equals to summation x of n e to the minus j omega n from n equals minus infinity to infinity. So this function here represents the Fourier series expansion of the periodic function x of ej omega. So x of ej omega has the Fourier series expansion of this, and these are the CNs actually, and you can think of those as the CNs in the continuous domain when we take it in signals and systems. As a result, the Fourier coefficients x of n can be computed from x of e j omega using the Fourier integral given by x of n equals to 1 over 2 pi. It's 1 over 1 complete period because it's a periodical function. X of ej omega is periodic. We take it over 1 period from minus pi to pi. X of ej omega e to the complex conjugate of this one. So this is j omega n d omega. So you integrate this function to find x of n. This is the time domain, this is the frequency domain. This is the time domain, this is the frequency domain. So in the forward direction, you go with this definition. In the backward direction, you go with this integral, and you get the inverse. So this is the inverse dtft or I dtft, inverse dtft. So we can say that x of ej omega equals to the Fourier transform of x of n or we can say also for the inverse that x of n is equal to f inverse of x of e j omega. And we can also represent this in form with 2 arrows, and we can say dtft x of e j omega. Okay? So all those different representation for the process of finding the Fourier transform or the DTFT of a discrete time sequence. Okay, I'm going to take an example here. Example, consider the Fourier transform H low pass of Ej omega equals to 1 for the magnitude of omega between 0 and some omega c, cutoff frequency, and 0 for the magnitude of omega between omega c and less than or equal pi. Actually, this function is the transformation or the Fourier transform of the impulse response of the low-pass filter. Low-pass filter looks like this. It has, so this is my H low-pass of Ej omega. And actually, this is a periodical function. This is omega c minus omega c, and this is omega c, and the 1. So you have here pi, you have here minus pi. This is the function here, but this function is periodic, which means that it will repeat itself actually around 2 pi. So you have another 2 pi minus omega c, 2 pi plus omega c, and you continue. And at minus 2 pi, you have also rectangular shape with an amplitude of 1 also, and this is minus 2 pi minus omega c minus 2 pi plus omega c, and this also continues forever. But we are interested in this to find our goal, which is the H low pass of n. What is the discrete time sequence that give us this type of impulse, or sorry, frequency domain signal like this? Okay, so what we need to find here, find H low pass of n. Okay, so this is our problem, and this is LP. LP means low pass filter. Okay, so the inverse DT FT of H low pass of E j omega is H low pass of n equals 1 over 2 pi integration over one period from minus pi up to pi. The amplitude is 1 e to the j omega n d omega. Sorry. If I put it 1, I have to put those from minus omega c to plus omega c. So this is from minus to plus omega c. Okay. So we just put the values. This is the from minus pi to pi, but we have zeros here and 0 here, so it's non-zero from minus omega c to plus omega c, and this will give us 1 over 2 pi e to the j omega n over jn from minus omega c to plus omega c, which is equal 1 over 2 pi times e to the j omega c n over jn minus e to the minus j cn over jn, and this will give us sine omega cn over pi n for n between minus infinity and infinity, and n does not equal to 0. So if you apply 0 here, you have 0 over 0. Yeah, we can say that we can solve it by the L'Hopital rule and find its value, but let us look at a little bit deeper on the values that we got. So if you have undefined value for n, so you have undefined value 0 over 0 for n equals 0. So we have for n equals 0, we have to go backward here and do the answer. So h low pass of 0 is equal to the 1 over 2 pi, the integration from minus omega c e to the j omega times 0 d omega. So you apply n equals 0, so this is equals 1 over 2 pi integration from minus omega c d omega, which is equal to 2 omega c over 2 pi is equals to omega c over pi. So our h low pass of n is equal to omega c over pi for n equals 0, and it's equal sine omega c over pi in pi n, omega c n times pi n for n not equal to 0. Now, some can argue that, okay, if you take this in the limit as n goes to 0, then it is equal to omega c over pi. Most of you know that by the sinc function, or the sine x over x. So this is omega c over pi by L'Hopital rule or by any other rule. So you can say that I have a compact form h low pass of n is equal to sine omega c n over pi n for n between minus infinity and infinity, and we do not include the 0 because it's already inside this one. We use this in computer, in softwares and algorithms. If you want to apply an algorithm and you put this form, then this one will give you a problem at 0 when the index is equal to 0. So you have to go for the 0 and define it here. So if you are using algorithms or you are programming using MATLAB or any other language, you have to define for n equals 0, this is h low pass of 0. And for n not equal to 0, this is your h low pass of n for any n that does not equal to 0. If you are just writing mathematics or you are doing some derivation, then you can use this formula with no problem. Okay? So with this, we come to the end of the definition of the DTFT, discrete time Fourier transform, and next lecture we will continue with the properties and theorems regarding the DTFT. Thank you very much. See you in next lecture.